today we're going to continue with our discussions relating to threading and synchronization in Android. And what we're going to do now and for the next class is start to discuss some of the patterns that underlie the Android concurrency idioms and mechanisms that we've been talking about. Things like handlers, messages, runnables, async tasks, and other capabilities like the looper. So speaking of the looper, we're going to start off by talking about loopers. So you may remember in one of the discussions we had fleetingly in last class, I mentioned how a looper, there can only be one looper per thread in Android. And if you take a look at the documentation, it explains that fact. If you poke around, by the way, on Stack Overflow, you'll see a lot of people complaining about there only being one looper in Android and running across problems. So if you ever run into problems with loopers, be aware that other people have run into them as well, and Stack Overflow has a lot of good discussion of this topic. So it's an interesting question. How might you go about ensuring that there's only one looper per thread? It's certainly a worthwhile design exercise to think about briefly. And if you think about it for very long, your first temptation might be to try to design some kind of looper registry. So as I show in this example here, we have a looper registry, which is a static hash map that's nestled inside of our looper class. And when the prepare method is called, the prepare method is the method that checks to see whether or not there's more than one looper. What we could do is we could go ahead and synchronize on the looper class. Because this is a static method, we can't use this. We'd synchronize on something that we know to be there, like the looper class. And then we would go ahead and we would look up in the hash map to see whether or not we already had a looper registered with this thread ID. So in this particular case, we have a hash map that maps thread ID, which is a long, to looper. And if we get back something from this get operation and it's not null, then that means someone's already registered a looper. And that's a no-no. So we can't do that. We have to quit first. We have to get rid of this. So in that case, we're going to throw a runtime exception and bail out and say, hey, only one looper can be configured per thread. If we don't find a looper pre-registered, then we go ahead and we add our looper. We make a new looper and we stick it into our looper registry under the thread ID. And then we release the lock in the synchronized block. OK, any questions, any comments about that particular solution? So arguably, it will work in the sense that it'll tell us if we have more than one looper. Oops, let's fix this problem. Yes, sir.
So as this looper is getting messages, and it's processing them, is it doing work on itself or on the other thread that passed that message? I don't really understand.
That's a really good question. So keep in mind a couple things. First of all, you can have only a single thread in your whole activity, in your whole application. And so you can do work, and then if you have something that's going to take a while to run, or you'd like to have it run at some later point, you can go ahead and post that or send that, and that'll end up going back into your own looper thread. So that's how you kind of defer things till future processing. So that's one way to do things. And if you're really gung-ho on not having threads, that's kind of how you program. That's a little tedious, of course, and it means you can't do anything that blocks for any length of time, because otherwise you'll get the dreaded application not responding exception or dialog. The other approach, which is what we've been talking about, and we'll actually talk about this further next class, is the concept of having multiple threads, the background threads, if you will, and they're doing stuff and they can block. And when they're done, they're going to pass messages from themselves in separate threads back to the main UI thread. And the way they would do that, there are various ways to do that, but one way they'd do that is they would take a handler that was created in the UI thread. So it had to have been created in the UI thread, and that's because we want it to be associated with the UI thread. And well, actually, that's another example of what we're about to talk about, is if you take a look at the handler implementation, it knows the thread it was created in. It keeps track of it in its constructor, depending on which constructor you use, of course. So in this case, other threads are doing work, and then they're handing the work through messages or runnables off to the looper thread, to the UI thread, which runs a looper. And that uses under the hood, we haven't really talked about this in detail, but under the hood it uses some kind of inter-process communication mechanism that goes and uses low-level descriptors and so on in order to move data from one thread to another. So that's typically how that works.
Yeah, it's much more clear. Thank you.
So think about it like this. There's various ways to think about this. We will talk at length next class about the active object pattern, which is a variant of what's used in this whole affair. But basically, you can think about a chef at a fast food restaurant where people like clerks or cashiers give the chef orders to fulfill. And so the chef might have a list of orders or a queue of pending orders. And so the cashiers would be responsible for taking the orders. Imagine like a Wendy's hamburger restaurant or something like that. The cashiers would be responsible for taking the orders. They're sort of like the handlers, if you will, or the threads. And then they go ahead and they use the queue interface, which might be as simple as taking a piece of paper and sticking it onto a revolving merry-go-round-like mechanism so that the chef knows what things to handle next. We'll talk more about that when we talk about active object. OK, any other questions about this particular approach? So the downside with this particular approach, yeah?
No, is it supposed to say ensuring one looper per thread?
Yes.
On?
Whoops, does it say on?
Yep.
Oh, ha. Let's change that. That's the kind of thing I would forget. All right. So any questions about the particular issues of the design? So the downside with this approach, of course, is that we've got synchronization taking place. So we could end up with a bottleneck, at least in theory. If you had lots and lots and lots of threads running loopers, they'd all be kind of coordinating here, and that could end up being inefficient. So the question is, what's a better solution to do? So the solution we're going to talk about, which is actually what Android does, so it's not just a good idea, it's actually what's done in Android, is to apply something called the thread-specific storage pattern. And this is realized in Java through something called the ThreadLocal class. And this basically gives you a seemingly global object when, in fact, the implementation of the object is specific to every thread of control. So it looks like a global object to the outside world, but when you access it, you're actually accessing thread-specific state. So here's an example of how this works. We'll look at more of this example later. We'll come back after we talk in more detail about how the pattern is specified and how the implementation in Android works. Basically, the looper contains a ThreadLocal object, which is a generic that's customized by looper. And as you can see here, what prepare does is it goes and it says, has anybody stored something into thread-specific storage yet? And if the answer is yes, then we're in trouble because we've already gone through and initialized ourselves. If the answer is no, this returns null, and so we're OK. And then we go down here and we create a new looper and we set it into thread's local storage. And what's interesting about this, as we'll see shortly, is that there's no locking operations required anywhere here. So all the locking operations are moved outside of the thread, and so there actually is no synchronization overhead at all. Even though it looks at first glance very much like the other example, right? It looks like you got an object and you're accessing it by calling get. In this particular case, what you're accessing is actually getting to thread-specific storage. So we're going to talk about that. It's a really interesting pattern. It's very cool, not very well understood, and should be used sparingly, of course, for the reasons we'll discuss. So take a look at the ThreadLocal HTML page on the Android site, and it'll talk to you more about what ThreadLocal is, and we'll talk more about that. OK, so this is not just a random assortment of classes and methods. This is a particular instantiation of a pattern. The pattern appeared in the POSA 2 book. It's called thread-specific storage. The intent of this pattern is to allow multiple threads to use one logically global access point object, for example, to retrieve instances of objects that are local to a thread, stored local to a thread, without incurring locking overhead on every access. So you don't have to incur the overhead of locking, but you're getting stuff that's thread-specific, and therefore capable of being used without having to worry about contention. And this pattern is used very, very widely in GUI frameworks and threads and threading frameworks. If you take a look here, it's in the POSA 2 book, but you can also take a look here and find the pattern online. And it's quite interesting. It's documented using C++, but it applies quite nicely to Java too. So when would you want to use this thing? Well, you want to use this thing if you want a concurrent program that is both easy to program and efficient, which is sometimes kind of hard to do. And of course, efficient means different things to different people. But in this particular case, what we want to be able to do is make it easy to program so it doesn't require all kinds of special purpose programming tricks, but we don't want people to have to know anything about locking. You just want to be able to access this stuff and have it be magically thread safe and atomic and so on. Often in life there's trade-offs, right? So they always talk about good, fast, cheap. Pick 2 of 3. Right? So here's a case where we're going to get simplicity of programming and efficiency. You don't always get that. Now, there are some limitations with this, of course, but we'll talk about that later. The original reason why people came up with thread-specific storage was kind of interesting. The original reason was people had a lot of legacy code that they'd written, which only had a single thread of control in it, and that code accessed global resources without passing parameters to functions. And what that meant was when people started to try to use this legacy code in modern multi-threaded systems, they had a problem in certain places. And we're going to talk more about this particular problem when we get to the known uses discussion. But one of the classic examples where this is a big issue is in the context of EraKnow. Does anybody know what EraKnow is? You'd have to be a sort of a C or C++ programmer to really know EraKnow, and you'd have to be sort of a systems programmer. Yeah?
It's the integer that holds the last error number returned by some operation.
That's right. So historically, what EraKnow is, it's a value that stores the last reason why something failed if something fails. And historically it was stored as an int, and it was a global int. And so if you wanted to access EraKnow, you just sort of said extern int EraKnow, and there it was. There's a huge problem when you start trying to use things like EraKnow in concurrent programs, however. And this example illustrates this. So imagine we have 2 threads, thread T1 and thread T2, and one comes along and does a receive operation, and for whatever reason that receive operation can't make progress because it's flow controlled, and so it gives back a -1 with the EraKnow value set to E would block, which says it would block if we were to actually wait on this thing. So it's flow control. Okay, and between the point when we return from receive and check the value of EraKnow, another thread comes along, also calls receive, which is a system call, and for whatever reason that got interrupted, so it got the EINTER EraKnow value set. Well, what happens here, of course, is if T2 is preempted and T1 starts to run again, T1 will say, aha, I have a -1 value for receive, but my EraKnow value is EINTER, and be completely confused because it's trying to access a global that is not protected by any kind of synchronization mechanism. Now, how might we fix this? Well, we might fix this the same way that we tried to fix the stuff earlier when I was showing you about the registry for loopers. But that is horribly broken, just hideously broken. Number one, it would require everybody to put locks around EraKnow. And number two, it really wouldn't even work because even if you'd have to put the blocks around the point where you made the receive call, and when it returned, you'd still have to hold the lock, and then you'd check EraKnow. So you'd have unbelievable contention in your program, and it would just be a big mess. So instead of doing that kind of stuff, people use thread-specific storage. And that way, each thread gets its own specific version of EraKnow, and so it can set it and check it at its leisure, never having to worry about contention or race conditions on that particular variable. So we'll talk a bit more about that later. OK, here's the structure and participants of this particular pattern. And it's kind of interesting because there's a bunch of toolkits that give you building blocks of some of this stuff, but they're somewhat unsatisfying if you don't do the whole pattern. So I'm going to talk about the different pieces in turn. The first piece we're going to talk about is something called the thread-specific object proxy. The purpose of this particular interface, class, element, module, and so on, role, better word, is to try to give people a nice high-level way of accessing thread-specific storage. So you don't have to take care of low-level details. Some frameworks, some programming languages make this easy. Other frameworks, other programming languages make it less easy. Java is somewhere in the middle. C is very much at the low end. You have to build all this stuff yourself. Java kind of gives you an intermediate thing. The ThreadLocal class is the thread-specific object proxy. The ACE framework, as we'll see later, has a really cool support using C++'s delegation operator. We'll look at that. So that's one piece of the pie. There's also something called the key factory, and that's used to make the ways to identify each of the thread-specific objects. We're not going to talk much about that. It doesn't really show up in Java. It's kind of hidden from you by the ThreadLocal class. The next thing, which is really the key workhorse here, is something that's called the thread-specific object set. This is a map or some kind of data structure that will take a key, which corresponds to the object that you're dealing with, and it will give you back a pointer to a thread-specific object. And we'll talk about how that works later. In the case of Android and Java, it's ThreadLocal.values. That's the thing, the data structure that keeps track of this.
Is that not similar to the registry idea that you were talking about?
It is, absolutely. The difference, that's a great question. So the question is, isn't this sort of like the registry we were talking about? Absolutely. The difference is that that registry that we saw was shared by all threads, and therefore you had to lock it. The thread-specific object set is either logically or physically local to a thread. So it's a map, but it's only in one thread, and each thread has one, typically. We'll talk about different ways to implement it in a second. Yeah, that's a great observation. There's a thing called ThreadLocal.values. We'll look at that momentarily. And then the last piece of the puzzle is the thread-specific object. This is actually the thing that does whatever it does, right? It's something that you're going to store in thread-specific storage. And the particular example we're going to talk about here, of course, is the looper. So that's what we're going to put in thread-specific storage. But of course, you could put other things in thread-specific storage as well. OK, here's the dynamic view. And there's a whole different variant. I'm just focusing in on a piece of this whole thing. If you read the pattern description, it'll give you more details of this. So typically what happens is here, you come along, depending on how powerful your thread-specific storage interface is in your language, and you invoke some method on an instance of a thread-specific object proxy. Now, the goal of this is to make it look like to the application developer that you're just making a method call on an object. They shouldn't have to know what's in thread-specific storage or what's not. You just want to make a method call and leave it up to the implementation to ferret out where the actual stuff resides. And we'll see how that works in a second. So you make a method call. Under the scenes, that goes and figures out what thread you're in, figures out what key you're associating this particular method call on, the object ID. And then it goes and it looks up in the object-specific thread-specific object set, and it gets you back a thread-specific object, and it returns it back to the proxy. And in certain cool implementations, like in C++ and in ACE, then it goes ahead and it automatically delegates the method call to the thread-specific object without you having to do anything else. So it just kind of magically forwards to the call. And then you get the result back. So that's kind of how things work. So you invoke a method on a proxy, it gets the underlying thread-specific object, and then it automatically invokes a method on the object. You'll see that Java doesn't quite go that far because Java doesn't really have anything quite like the delegation operator in C++. But I'll show you that also. It's pretty cool. All right, so how does this actually work under the hood? What's the technique? So there's a couple things you got to think about. First thing you got to do is implement some kind of thread-specific object proxy. And this is the guy that mediates the access to the underlying framework that keeps track of all these moving parts. And essentially what you're doing is you're defining an interface for a variable. It looks just like a regular variable object, but each instance of it is stored in a thread-specific way. There's a couple different ways to do this. In ACE, we do it by having a template class that's parameterized by the type you want to make thread-specific. And it uses the C++ operator arrow, which is the so-called delegation operator. And I'll show you the implementation in a second. Other technologies work a slightly different way, but you need to define it somehow. The next thing you need to do is implement the thread-specific object sets. And as Sean pointed out, there's a couple different ways to do this. One way to do this, which is typically the way things work if you use thread-specific storage that's actually implemented as part of the runtime system of your threading library. Right? So if you're using like Java threads or you're using POSIX-P threads or something like that that has this built in, then what they'll typically do is they will reserve some space or a pointer to store some space in each thread control block. So every application thread or every thread you have has some space that it's used to hold the thread-specific storage map. So that goes back to what you were asking. Each thread has its own map as opposed to sharing them. So that's one way to do things. And that turns out to be very efficient for a variety of reasons. The other way to do it is to have external thread-specific object sets. You would typically do this if you were trying to emulate thread-specific storage in an environment that did not natively support it. For example, some earlier implementations of embedded operating systems, like early versions of VxWorks, lacked thread-specific storage. Other implementations of things like Windows have really goofy thread-specific storage, where you only get a very small number of thread-specific storage objects per thread, like 32 or 64, some small number. So in those environments, you may have to emulate this. In that case, you would have some kind of data structure, and then you would mediate access to it. This is obviously less desirable, though, because you end up with some locking overhead. Then you have to figure out these data structures that map things appropriately. And there's sort of two things you got to think about. One is, how do you map the keys to thread-specific objects? And the other is, how do you map the thread IDs to thread-specific object sets? So there's two parts of this thing. So typically what you do, the most common way to do it, is you have this data structure on a per-thread basis. And if you have a fixed number of thread-specific objects per thread, you might have an array of these things. So you might have an array of 64 or 32 thread-specific slots you can store thread-specific objects in. The nice thing about that is it's super fast, because it's just an index. The key is just an index into that table or array or vector. If you want to support a much larger number, then you're going to have to use a data structure that's capable of expanding. And the most common thing to use there is some kind of hash map. So that's another way to do it. You could store a hash map, and so you would look things up and find the thread-specific object that was stored here. So leaving aside implementation details from a logical point of view, each thread-specific object, or each thread-specific object proxy, corresponds to a row in a two-dimensional table, and each thread corresponds to a column in this table. And when you have a particular object in a particular thread access a particular key, that tuple will get you to a pointer or reference to the thread-specific object. Now what's interesting about this is that the object itself could actually be any old object. So the object isn't necessarily thread-specific. It's the access to the object that's thread-specific. Now, 9 times out of 10, or 99 times out of 100, the object you're accessing is only accessed by that thread. But if you really wanted to be perverse, you could make a pointer to some global object and stick it in this thing. It would be a bad idea, because it would defeat the whole purpose of having thread-specific storage. But it's not really the object that's thread-specific. It's the access to the object that is being thread-specific. So it's that combination of things. It's the thread ID, it's the particular object, it's the key, it's the proxy, it's all these things that collaborate to get you to the specific object that you care about. All right, so let's take a look and see how this particular pattern is actually implemented in Android, now that we've sort of talked about the various pieces. So there's this class called ThreadLocal, and that implements the thread-specific storage pattern, or a variant of it. The main difference is that in Android, it doesn't give you the full-blown proxy. So in the C++ versions we were talking about with delegation operator, you can have a full-blown proxy. You invoke a method on that proxy. It goes in under the hood, grabs the thread-specific object, and then redelegates to it. In Java, you can't quite do that. So what you have to do is you first have to call get on the thread-specific object proxy, which is really more just like a wrapper. It's not really a proxy at this point. It's just an interface or a class with some methods put and get. That goes behind the scenes, gets the underlying thread-specific object, and returns it to you. And then once you've got that thing, then you make a method call on that thread-specific object. So notice you have to do 2 calls here in the Java model. Whereas in the full-blown pattern, all you have to do is make 1 method call. It gets the thing for you and then delegates it automatically. I will show you how to implement that in just a second, just so you'll know. All right, so that's one part of it. And if you take a look at the ThreadLocal header file, you'll learn more about that. So all threads share the same ThreadLocal object. So thinking about our looper example that we had before, you're going to have the looper, and it's going to have the get method on it. So you go get the looper. And what that's going to do is it's going to, in this case, it would be the ThreadLocal object that we had defined specifically for our particular use case, or Android has defined specifically for their use case for the looper. And in fact, let's just take a step back here and see what that was called. That was called sThreadLocal. So if you come back here, so it's really more like sThreadLocal : yeah, that's a little bit more like what it's actually doing. I'll come back and fix all that up later. But what that says is that that's the particular thing that's playing this role. And then each thread that calls the get method is actually going to get back a different object. So one thread versus another is going to get back a different looper, for example. So internally, and we'll look at the implementation here in a second, the way it works is that there's this data structure called values. It's a struct or a class, and there's an instance of this thing called local values, and every thread has that, and so that's used to actually keep track of the thread-specific data, and it uses a hash-like mechanism, which we'll look at in a second too. And then the last thing is, by you put all those different pieces together, it'll find you the looper that we want. Okay, so if you actually look at the code, it's kind of cool, and I'm going to show you the code here. Well, first I'll tell you about the code, then we'll go look at it. So ThreadLocal.set figures out what the appropriate values map is, in other words, the one that's for that thread, based on the current thread ID. So if you look here, it says, what thread am I in? I'm in the current thread. And then it goes and it looks up in the current thread, and it gets back this list of values. And assuming it's not null, then it goes ahead and it does a put operation on that particular values array, storing the value that was passed in here under this for this particular object. That's it's going to be its key, essentially. All right, and notice there's no synchronization. If you look through this code, there's no locking at all. That's the beauty of thread-specific storage. So let's go over here and take a look at the code. It's somewhat instructive to do this. All right, so let's take a look at set. So this is just the code we just looked at. Here's the code for set. You can see what it does. If you take a look at things like what's values. So what values does, oops, that's initialize values. So what values does is it goes and it takes a look at the thread, and it says, give me your local values. So if you take a look at thread, so there's thread. The thread class's local values data member is a ThreadLocals.value object. And if you go back over here and you look for values, here is values. So it's a per thread map of thread local instances to values. This is the whole thing is sort of strangely recursive. And you can see that they start out by picking an initial size, 16. They always are powers of 2. And there's something called tombstone, which I think they use for deleted. When items get deleted, they recycle them. And then if you look down here, there's just a bunch of code that does various things. But this is basically how all the different implementation parts work. And I think if you take a look here, there's a method called put, or there we go, here's put. So put takes a thread local key, which in this case was this, and a value, which is whatever we're going to store, like the looper, for example. And it basically goes ahead and does some operations to store things into the map. And there's a whole bunch of different things that they do. And there's also stuff that they do, which we'll see in a second, in the case of the other operation that's defined. OK, so that was set. And then there's get. So get's a little bit different. It's a little bit more complicated. It uses the same technique of basically figuring out what thread it's in, going and getting the thread local map, if you will, from that particular thread. And then it's got some more stuff that's going on. Let's go take a quick look at that. Basically, if you see here, let's take a look at get. So get is optimized for the fast path. And as you can see, it tries to look some stuff up and see if it's already available in some kind of cache. And if it's there, it just goes ahead and directly indexes into it. So it's very fast. If it's not there, then it's got this method called get after miss. And this is more complicated. It has to do more things. So you can see it's basically going to search through the table. So it takes longer to do that. So basically, it kind of has this optimized for the common case or the pattern of trying to locality of reference or things that have been accessed recently. We want to cache them so we can get back and get them quickly. So that's why you might find if you have lots and lots of thread-specific objects, they might perform differently over time as you run them. OK, so that's the thread local implementation. Now, how does this stuff get used? Well, this goes back to what we looked at before. You can see that the looper class uses a ThreadLocal object in order to make sure that there's only one looper. We looked at that before. No locking overhead that goes on there. There's also a bunch of helper methods that are part of this implementation that are used to get the thread-specific looper. So this is kind of an interesting one. This is one that's called myLooper, and myLooper gets used in various places in the looper implementation. So you can see in the looper implementation, and this is odd. I think I know the reason why they do this, and we'll see if you guys know too. They have something called message queue, which is a data member in the looper. You can see it right here. And then the loop method, remember loop is what actually runs the event loop. That's the thing that sits there and waits for incoming messages on the message queue and dispatches them to their target. The first thing it does is it goes ahead and says myLooper, which goes and gets the thread-specific looper that this guy's associated with. And if it checks to see if you've even been initialized. If you've never initialized a looper at all, you haven't called prepare, for example, and then you try to run loop, it's going to blow up. And then look what it does. It goes ahead and it takes the thread-specific looper that it fished out of thread-specific storage, and it grabs that guy's message queue, and it stashes it into this local message queue. Right? So this is weird. There's this message queue up here, and that's what's being accessed here. And then we go ahead and we cache that into a local message queue. Does anybody want to speculate why we do that? And then the rest of the looping operations are done off of that. I think it's just locality of reference, moving things into closer variables that can be optimized better, and so on and so forth. If we take a look over here at the code for this thing, so here's the looper. Here's the looper's loop method. So it grabs that guy, it goes and stashes it away, and then it just sits there and blocks in that particular place. Don't show me this message again. Thank you. OK, so this is the looper. Take a look at myLooper, for example. You can see where it gets used. Basically, anytime you want to refer to the looper, then it calls myLooper. And myLooper, as you can see, just goes ahead and fishes the data out of thread-specific storage. And we use that all the way through whenever we have to refer to the current looper that's being accessed. This also, of course, allows us to be able to use static methods because we can fish out this thread-specific looper because it doesn't live in an object, it lives in a thread, not in a specific object. I had mentioned earlier that there's also the handler stuff as well. Let's see, I thought the constructor, yeah, check this out. So you can see here that the handler method, remember that this goes back to what you were asking, Nolan. So handlers, when they're created based on this constructor, there's a couple of different constructors that they have, but like the default handler constructor. Notice what it does is if you don't do anything else, it goes ahead and it says, hey looper, give me back my looper. So that's going to get you back the thread-specific looper. So if you create an object handler in a thread, it's going to live, it'll be owned by that thread, and its constructor makes sure that that happens. So make sure you're careful where you create your handlers. Make sure you create them where you want them to live and not create them in some other place. OK. So that's basically the way it's done in Android. Here's the source code. So let's talk about the pros and cons of this particular pattern. So the good news is it's efficient in the sense that you don't need to have locks in order to access the state, the data. It's relatively easy to use. As you can see here, it's pretty much like programming regular Java code. It's instructive at some point in your life to try to figure out how to program thread-specific storage using the low-level C POSIX pthread API, which is unbelievably convoluted. We'll see a little snippet of it in a second. And you'll see why it's much better to have wrappers and proxies to save your life. Speaking of wrappers, you can combine this pattern with wrapper facade, which is a pattern. It's another POSIT2 pattern. We'll talk about it later, in order to be able to get portable access to low-level system call APIs, which makes your code more portable, makes your code more reusable. So that's a benefit. Java does that. All the Java class libraries are wrapper facades. There's some downsides, however. Probably the main downside with this approach is it ends up encouraging people to use globals. Even though they're thread-specific globals, they're still logically globals, and that has all the common downsides with globals? What's a good example of a common downside with a global? What are things, why are globals considered bad? Why do they make you go like this?
Coupling.
Coupling. You end up being coupled to a particular context. And so when you try to move your code, you can't just move a piece of it, you have to move the whole thing, and everything that the globals, that accesses the globals have to come along with the other parts. So it makes things much more tightly coupled. It also means when you change stuff that's related to a global, you run the risk of breaking a lot of things because they depend on it in an implicit way. It obscures the structure of the system, so it hides things. It's like fog or a smoke screen or pollution or something like that. You can't see as clearly what's going on. That's kind of another way of looking at coupling and unwanted dependencies. And of course, if you have a really inefficient implementation of looking up your thread-specific objects, then it might not actually be any better than grabbing a lock, although it might scale better if you had lots and lots of threads. So that's an implementation consideration. But if you have really, really inefficient things like linear search through the list of thread-specific objects, that could slow you down quite a bit. OK, so there's a bunch of known uses. The best example of known use in my mind is EraKnow, which once multi-threading became popular was widely implemented as a macro that turns into a call to thread-specific operations so that you don't have to worry about the race conditions that would otherwise occur if you were sharing global EraKnow variables between threads. And you can read more at the Wikipedia link about what EraKnow is. And it's just interesting to know. I should probably show the implementation of it. It's kind of cool. ACE has a really cool implementation of this pattern, not surprisingly, because we wrote the pattern originally based on what we were doing in ACE and found other known uses to make it a pattern. So it defines a class called ACE-TSS. And ACE-TSS converts, it's a template, and it converts its parameter into something that is easily accessible in a thread-specific way. And it also, of course, provides nice portability to different platforms. If you read the paper here, it talks about the ACE implementation. The way it works under the hood is it uses this really cool C++ operator called operator arrow, the so-called delegation operator. Can anybody explain the delegation operator? Does anybody know how it works?
So anytime you say whatever on the left arrow, some method, it will actually go in and execute your code first. But you can actually start chaining it if you return something that's not of the pointer type, but also overloads that operator.
Yep. So it's really subtle. And when you first see it, it makes no sense whatsoever. But I'll break it down and show you. So here's a little snippet of code from the ACE-TSS class, the most important piece. This is the operator arrow method. This is the delegation operator. And you can see that this thing is a template class. It returns a pointer to the type it's parameterized with. And when it's called, these are those hideous, low-level C-style thread-specific storage APIs, which nobody in their right mind wants to program against, by the way. So what it does is it comes along, and it would have cached this key underscore in its constructor somewhere that uniquely identifies the specific object we care about. And it says, hey, is there any data? Is there a pointer that's previously been initialized for this particular key in this particular thread before? And if the answer is no, then it goes ahead and it makes a new one. It creates a new thread-specific instance dynamically of type. And then it says, go ahead and set that thing into thread-specific storage. So it dynamically allocates the type if it doesn't already exist, if the object doesn't already exist, and it stores it in that thread in its thread-specific object set. And when it's all done, it returns the pointer to the allocated object. So either you allocated it this time, or this is a subsequent time through this particular code, and so it just returns a reference or a pointer to it at that point. So what comes back from operator arrow is a pointer to an object that resides in thread-specific storage. And then what you typically do is, as Christoph correctly noted, when you call a method like this, let's say that we have a class called requestCount that's just going to keep a count of something. And this is not thread-safe code. We create an instance of ACE-TSS called requestCount. So that's a variable of type ACE-TSS parameterized with this particular class. And then when you say requestCount arrow increment, it first calls this method here, which is the delegation method, which gets you a pointer by hook or by crook to the thread-specific data. And then it returns it, and then C++ automatically delegates to the increment method. And so that goes ahead and calls it So it looks like just a regular function call, but in fact it's actually accessing data that's stored in a thread-specific way. So it's very cool, very powerful. All right, so to summarize this, Android implements thread-specific storage via the Java ThreadLocal class, which doesn't give you the whole full-blown mechanisms that you've got in the thread-specific storage pattern, but it gets you most of the way there. And Android uses this in order to be able to get access to, or in order to ensure you only have one looper. It also is used for the handlers, as we were talking about before. All right. Any questions?